Welcome to Inverse Matrices. Hi, I'm Carolyn Heiss. I'm the Math Department Chair at Georgetown High School. I teach AP Calculus AB and BC and Independent Study in Math. Did you know that the work of many mathematicians was required to develop the concepts of inverse matrices and their applications? Gottfried Wilhelm Leibniz, who lived from 1646 to 1716, worked on the development of determinants. Gabriel Cramer, from 1704 to 1752, developed Cramer's rule. Carl Friedrich Gauss, from 1777 to 1855, developed Gaussian elimination. Augustin Louis Cauchy, from 1789 to 1857, worked on the development of properties and notation and applications of matrices. Arthur Cayley, from 1821 to 1895, developed matrix theory and the Cayley-Hamilton theorem. And lastly, James Joseph Sylvester, from 1814 to 1897, further developed matrix theory, broadening and formalizing concepts. He worked alongside Arthur Cayley. In this presentation, I'm going to introduce inverse matrices. First, we'll examine the definition and the formula for inverse matrices, as well as some properties of inverses. Then we'll look at why the formula works and at inverses of larger matrices. And finally, we will use matrices to solve matrix equations. Introduction to inverse matrices. What is an inverse matrix and how do we find it? Let's look at some properties of inverses. So an n by n matrix A is invertible and non-singular if there exists an n by n matrix A inverse such that A times A inverse equals A inverse times A equals I sub n, where I sub n is the identity matrix of order n. That is, it would be an n by n matrix. The matrix A inverse is called the multiplicative inverse of A. Now, do all matrices have inverses? No. A matrix that does not have an inverse is called non-invertible or singular. Non-square matrices do not have inverses, and not all square matrices have inverses either. A matrix must be square and have a non-zero determinant in order to be invertible. Here's the formula for the inverse matrix of a 2 by 2 matrix. If we start with the matrix A, B, C, D, and we want to take the inverse of that matrix, first we find the determinant, 1 over A times D minus B times C. 1 over the determinant. And then we multiply it by this matrix where we switch the A and the D and keep the C and the B where they are, but change their signs. Here are some properties of inverse matrices. A inverse inverse equals A. A transverse inverse is the same thing as A inverse transverse. K times A inverse will be the same thing as 1 over K times A inverse for any scalar value K not equal to 0. The product AB inverse is the same as B inverse times A inverse. The product ABC inverse is the same thing as C inverse, B inverse, A inverse. And we can have many more, A sub 1, A sub 2, and so on to A sub n inverse will equal A sub n inverse times A sub n minus 1 inverse, and so on, A sub 2 inverse, A sub 1 inverse. A to the nth power inverse is going to equal A inverse to the nth power for any value of n, which is an element of the positive integers. If A is an invertible matrix, its inverse is unique. Now, why does the inverse matrix formula work? Is the inverse matrix formula magic? We want to know how to find inverses of matrices. Matrices of varying sizes also, not just 2 by 2s. So let's take a look at another matrix here, matrix A, 1, 2, 3, 4. If I want to take the inverse of matrix ABCD, I'm going to use that formula that I showed you, 1 over the determinant times this D negative B negative C A matrix. So I'm going to take my 1, 2, 3, 4 as the elements of my matrix and put them in the appropriate places in the formula presented and simplify until I get the inverse matrix, which turns out to be negative 2, 1, 1.5, negative 0.5. We can check this by testing to make sure that our original matrix A multiplied by our inverse matrix is equal to I sub n. And this should work regardless of the order. So if I would have started A inverse times A, that would also equal I sub n. So we're going to check to see if we do get a 2 by 2 identity matrix by multiplying our original matrix A times the inverse that we found using the formula. So we're going to apply matrix multiplication, multiplying the first row times the first column to get the first element, the first row times the second column to get the second element, the bottom row times the first column to get the third element, and the bottom row times the second column to get the fourth element. Simplifying gives us our inverse 2 by 2 matrix. Now, here's another way to find the inverse matrix, which may be a little bit more of showing you the reason why this formula ends up working. If we take our original matrix and we append the identity matrix, we can use row operations to transform our original matrix into the identity matrix, and then the matrix on the right side will be our inverse. And this shows us how matrix multiplication is the reason behind the inverse formula working out the way it does. So we're going to use row operations to change the 3 down here into a 0. So I'm going to take 3 times our row 1 and then subtract row 2 to get our new row 2. And we do this to this whole 2 by 4 matrix. So our row operations now will change the upper 2 into a 0. So in order to do that, I'm going to take row 1 minus row 2 to get my new row 1. Here's the result of that. Next, I'm going to use row operations to change the 2 in the bottom right corner here into a 1. So I'm going to take this row 2 and divide it by 2 or multiply by 1/2 to get my new row 2. Now I see the identity matrix over here on the left side, and this is the same inverse matrix that we got using the formula previously, negative 2, 1, 1.5, negative 0.5. So this is the identity matrix. This is A inverse. We get that same result, which we've already checked to make sure that when multiplying our original by this inverse matrix, the result comes out to our identity matrix. Now, here's the formula for the inverse matrix of a 3 by 3. This is 1 over its determinant, and then we can arrive at these by looking at patterns of removing the row and the column of each respective element that we want to work with and finding the determinant of the remaining elements in the matrix, and then applying an alternating sign pattern where the middle of the top row is negative, then we have negatives on the outer 2 of the middle row, and then again the middle of the bottom row. So let's use this formula to find the inverse of matrix A. We're going to do the matrix 2, 1, negative 2, 5, 3, 0, 4, 3, 8. So here we've substituted each of the elements of this matrix into the formula that I presented you with. And simplifying produces this result. Further simplification, and we've got 1/2 as the value, the scalar value that we're going to multiply into this matrix. half of those values is presented here. This is our inverse matrix. 12, -7, 3, -20, 12, -5, 1.5, -1, 0.5. We can check to ensure that we've done this correctly by multiplying our original matrix by the inverse. And again, this should work regardless of which matrix is listed first, the inverse or the original. The product should equal our identity matrix of order 3, a 3 by 3 identity matrix. So we're going to check to see if that happens. Applying matrix multiplication, taking our first row times our first column to get our first element, and proceeding through our matrix multiplication, which we've learned previously, and simplifying does indeed give us our identity matrix of a 3 by 3 size. Now, there's another way to find the inverse matrix, similar to the second way that we showed earlier for our 2 by 2s. We can take our original matrix and append the identity matrix to it, and then apply row operations until we get the identity matrix on the left, and then our inverse matrix will be on the right. This will require a few more steps than the 2 by 2 though. So in a few instances, I'm going to do 2 row operations at the same time. So if I take my first row and divide each element by 2 or multiply by 1/2, I'm going to get my new row 1. That gives me the 1 in the upper left, which I want to make my identity matrix. Also, on the bottom row, I am going to start with row 1, multiply it by a -2. That's going to give me a -4 here, and then add it to row 3. So this will be a 0, which I also need in order to start working towards that identity matrix. And you can see the result right here. Next, I'm going to take my middle row, and my first row, and I'm going to multiply it by -5 and add it to my row 2. That's going to give me my new row 2. And the reason I want to do that is to get a 0 right here in this first column. So now my first column matches up with the identity matrix. Next, for my new row 1, I'm going to take the original row 1 and subtract row 2. And the reason I want to do that is to create a 0 at the top of my second column, which you see here. Then on row 2, I'm going to double the row 2 because my 0.5 then will turn into a 1, which I also need to get that identity matrix. Then I'm going to take my row 3 and subtract my row 2 so that I get the 0 right here that I need for my new row 3. Next, I'm going to take 3 times row 3 and add it to row 1 to get my new row 1. And that will make 2 times 3 give me a 6, and adding it to this -6 produces the 0 that I need in the upper right corner. Next, I'm going to take -5 times row 3 and add it to row 2 to get my new row 2. That will make the 0 right here. It's 2 times -5 is -10, added to 10 gives me 0. And I'm also going to take half of row 3 and make that my new row 3. So that will change this 2 into a 1 when I multiply by 1/2. So now I've got my identity matrix on the left and my inverse matrix on the right. Now we can use the principles of inverse matrices to solve matrix equations. In order to solve equations with inverse matrices, we might start with a equation such as matrix A multiplied by X is equal to B. Then we can multiply by the inverse matrix on both sides. Multiplying A inverse times A will give us the identity matrix, and multiplying the identity matrix by anything just results in that thing, kind of like multiplying by 1 with real numbers. So X is equal to A inverse times B. If A is an invertible matrix, then the system of linear equations AX equals B has a unique solution given by X equals A inverse B. So here's my matrix equation. 3, -1, -4, 2 is my matrix A, times my unknown x1, x2 matrix is equal to my matrix B, -5, 8. So my first step is going to be to find the A inverse matrix. So I'm going to use the formula 1 over the determinant, which is 6 minus 4, and then multiply it by this rearranged matrix where I've swapped the 3 and the 2 and changed the signs on the -4 and the -1. So I have 1/2 times this matrix, and that gives me the inverse matrix 1, 0.5, 2, 1.5. Second, I'm going to multiply both sides of this original equation by A inverse. But when I multiply A inverse times A, I get the identity matrix. So this just leaves my matrix X with elements x1 and x2 equaling the inverse of A times B. So using matrix multiplication, I arrive at this answer, x1, x2 is equal to -1, 2. I can check by substituting this back in for x, using matrix multiplication, and checking to see that I do get matrix B, -5, 8, which does work out. Mathematics is the music of reason. This is a quote from James Joseph Sylvester, who worked on matrices most recently in the development of matrix mathematics. Matrices are used in a lot of fields in modern day. These are projected market sizes by the year 2027, if not sooner. Machine learning is a huge one, comprising approximately $725 billion of the market. Data science is not far behind at about $675 billion worth of the market. Computer graphics, image processing, cryptography, engineering, finance, quantum computing, and scientific computing also registering over $1 billion, but not quite as much as some of the other fields where matrices are used. Learning about matrices opens doors to your future. Thank you for watching my presentation.